So good afternoon, everybody. So today we begin to learn about the synchronous generator. So far we learned about the transformers and the induction motors. So the difference between these three machines, we can simplify that as one. For the transformer, it involves so-called primary and secondary coils. Both are fixed. So while the primary be applied with the electricity, the secondary induced electricity, but with different voltage on it, with the same frequencies. So this is the transformer. Then, so for the induction motors, it also involves two separate coils. One coil is applied with the electricity. The other coil is movable, parts, that's the rotors. So for the stator side, if it is applied with the electricity, then there is magnetic field produced. As the secondary is movable, so the secondary, if not moved, there is a big magnetic field. Therefore, the current induced on the secondary. So the induced current on the secondary produce the secondary magnetic field, which interacts with the magnetic field induced, produced by the primary. So in the actions between the secondary and primary, so produce a so-called torque force, magnetic force. So it is that this magnetic force that drive the motor's rotor to move. As the motor's rotor moves following the force directions, so the relative movement between the motor stator and the rotor becomes smaller, and then the induced current on the stator becomes smaller. Therefore, the induced force becomes smaller. So the acceleration of the motors becomes smaller. So at the end, there is a balance between the induced motor and the induced torque and the torque required to move the rotors. So that's the balanced rotating speed of the motors. So from this point of view, we call the motor as the rotary transformer. So we can, based on cyclic concepts, to draw the equivalent circuit on the motors. Now we come to the generator. So largely speaking, that the generators physical structures very similar to transformer, but the shape is quite different. So now we come to see what happened to the generators. Okay, so similar to the previous two chapters, for the generators, we start with the starting of the constructions. I mean, the configurations of the generators. Then, based on the configurations of the generator, we're talking about the operating principles of a typical commercial generators. So with that in mind, we can further using our knowledge on the transformer and the induction motor to draw the so-called equivalent circuit. Then to carry out analysis about the performance of the generators based on the equivalent circuit. And finally, so we talk about the testing of the motor as well as the performance of the generators. Now go ahead to see about the first issues about configurations of the generators. Here we have a drawing of a typical physical configurations of the generator. Before I talk it in detail, I would like to tell you that generally for the generators, we must understanding mechanically. So very similar to the motors, the generator has two important parts. The first part is the stator. The second part is the rotor. So the rotor the purpose for the electrical power inputs, mechanical power inputs. So mechanical power inputs, you know that for the mechanical power for the generator, so the movement usually is the rotation. So the rotation speed, okay, that is the omega. Here we're using the W to represent it, is the input omega. And also the torque. So the input powers, okay, rotation speed, and the input torques. Okay, so this is mechanically. Electrically, they have the field coils. This one to produce to provide a magnetic field, a B with a current Okay, so this is the field coils. Armature coils. Outputs electricity. So this is the output powers. So the electricity, of course, is the the voltage and currents. So if it is three-phase one, of course, that will be three-phase root 3, 9, or 3 times three-phase. 3 times the phase voltage, the phase. Okay, here, so from the mechanical, so structures, there is so-called stator. The stator, means that not moves, fixed. The rotor, both the stator and rotor serves as the core materials with the core materials. Okay, so mechanical, stator, so there actually has the core materials. You know that core material is very heavy, which is the so steel custom steel materials that provide a good magnetic path. And the rotor also contains, so core materials that provide a good reactance for the magnetic field. And for the rotor, generally, so the rotor, which, is the input points of the mechanical powers, rotations. So if the mechanical power is the rotation that provided by the engine, they're usually, so the input powers, so the rotation speed in radians per second, omega, and the input torques T. Electrically, so there are two coils, very similar to that of the transformer. So the field coils, exactly speaking, the field coils here, we can say the magnetic field coils. The purpose of this one is to provide a constant magnetic field with a DC current or a magnet. Anyway, here the field coil, the function is to produce a constant magnetic field. You can use a whatever method to produce a constant magnetic field here, no matter which method you use. Okay, so you can use a magnet, you can use a right current to produce a magnetic field, that making the field be a constant. So whatever method you can take in. This is the field coils, armature coils. So the armature coils is used for the output electricity generated by the generators. Okay, so now you look, the rotor for input mechanical energy, the armature coils for output electricities. The problem is that how to combine the stator rotor with the field coils and armature coils. So you can imagine, so there are several ways. Okay, so in the picture below, actually we use this one. So one is that we install the field coils on the stators and with the armature coils on the rotors. The other one is that we install the armature coils on the stators with the field coils on the rotors. So both are okay. Depends on needs, right? Depends on needs. So in such a way, we can configure whatever generator. Now, let's looking at these diagrams to see how the generators works. Now, first, generally, a big generator requires a big field current, a field, big field coils, magnetic field, so that to generate a big output electricity. So, however, to produce a big field, magnetic field, we have to use a big magnet or a big field currents. So if we use a big field currents, that means that we're using another generator to generate a big currents. Therefore, for a big commercial generator, it usually has two sub or small generators. One is the so-called exciter. So exciter used to generate the necessary currents that to produce a strong magnetic field. Another one is an alternator that used to generate the output electricity for use. Now look at here for the exciter. Exciter actually is a small generator, which look at here. There is a stator marked here, stationary field, stator here, so which has a north pole and a south pole. So on the stators, it involves the two magnetic poles, north pole and south pole. How to produce a north pole and south pole? There are two methods. One is using the permanent magnet. So you can install a permanent magnet on the north pole and the south pole to produce a constant magnetic field. Another way is that we're using some of the batteries and coils so that we can produce a constant magnetic field between the north pole and the south pole. So here we use the pilot exciter to represent that whatever source you use here. You can use batteries here. You can use another small generators here. So anyway, we have a DC voltage, therefore a DC current supplied to the stators. On the stator, we have one group of coils here. So when there is current, there is a magnetic field, as we learned in last semesters. So we apply a DC current, say small 1 amperes. Here we produce magnetic field here, 1 Tesla here. For example, so 1 amperes current here. For example, 1 amperes. So we have 1 amperes here. So we have magnetic field here. One Tesla. Okay, so we are using 1 k amperes to produce 1 Tesla here. So now, here is stator with field coils. Rotor with armed coils. So here, okay, the rotor with armed coils make him visible, all right? So that's the right structures here. So on the rotors, there are several right three-phase or whatever group of the coils that cross the magnetic field. So this is the rotor. When the rotor moves, when the rotor moves, the rotor coils cutting the magnetic field produced by the stator here, therefore induce current on the rotors. Okay, so we have the rotors. So using 1 amperes, for example, here, produce 1 Teslas, for example, here, then the rotor with the armature coils on the rotor cutting the magnetic field produced by the stator generate the current on the rotor coils. So generate generate Rx equal to, for example, 10 amperes. So we're using a small generator here that generate the 10 amperes on the rotor itself. The here, because the under whatever conditions, the internally generated voltage or current are AC current. So once we're talking about generation, the generated voltage or current about whatever generator internally are AC one. Okay, are AC ones. Okay. Okay. Therefore, here we're using the so-called bridge rectifiers, which is a kind of the electronic circuits bridge using the transistors. Okay, using the transistors. So diode or transistors or whatever. So to making the AC currents or voltage change into the DC currents or voltage. Okay, so here is the rectifiers making the internally generated AC components become a DC one. So here we have the DC currents, equivalent currents that 10 amperes be generated here. Now, so here is the alternator, the major parts of the generator, which on the rotors there is a big AC current, a big DC current supplied to the field coils. Okay. So we have a field coils on this side. We have field coils on the rotors with a big current, say 10 amperes. On the stators, so the stator armature coils so we have the armature coils on stators here. Because we have a strong magnetic field generated here. Okay. For example, because we have the 10 amperes here, so we generate magnetic field be 10 Tesla here, and the output current and the voltage will be very higher. Okay, that's the meaning of it. So we have a constant magnetic field generated on the rotor or coil fields, which is installed on the rotors. As the rotors rotated, making the stator coils or the armature coils cutting the magnetic field produced by the rotors. So if the rotor has a constant rotating speed, making the cuttings be theoretical cuttings, rotating cuttings, which generate rotating magnetic field there, which generate the AC voltage on the stators. So we have the armature coils on the stator that has the AC three-phase AC outputs. Depending on the arrangement of the coils on the stator, so it may be a single-phase one, three-phase one, even six-phase one, depends, right? But generally, in practice, we use the three-phase because the three-phase is economically, so good. Okay. So this is the structures and the explanations on the functions of each part in these figures. So hope you understand the parts functions of it. It's about the stator, rotor, armature coils. Okay, they have different functions of it. So anyway, so for the generators, one, we need an external small DC current to generate a constant magnetic field. This is the first one. Okay. Second one, we need movable or rotors to receive mechanical powers. This too is the necessary inputs. Okay, so we need external DC source to generate big magnetic field. So to establish a constant big field. And we need this wire to input a big powers. It's the mechanical powers. Okay, this is mechanical powers. Okay. Then, so the magnetic field intact, rotate, right? Because of the rotation, magnetic field, and the rotation to generate electricities. I still remember that how to generate electricities with the magnetic field rotated in the magnetic field, with the conductors rotating in the magnetic field. Actually, we have learned these principles in chapter 3 in electric theology in last semesters. Okay, I will not explain in detail about this one, but here just showing you that we're using the DC generated magnetic field, which is strong, and we have the mechanical power inputs. Okay, so because the rotation and the magnetic field in the magnetic field, there is inductions. Okay. Now we come into the to looking at internally how does the coils, field coils, armature coils be arranged on the rotor and stator respectively. Here so has a look at the possible electric connections about the stators and the rotor coils. Similar to the generator motors. So for the generators, main has several different poles on the field coils, because we the pole numbers and the rotational speed together determine the generated electricity frequencies. The field pole numbers okay. In the motors, we can change for the given frequencies. We can change the pole numbers to determine the rotation speed of motors. Here, inversely, that the field pole numbers and the rotation speed together determine the frequency of the generator. Okay, so in the motor, the field pole numbers, the pole numbers on the stator, and the frequency of the applied electricity, determine the rotation speed. Okay. But here, the field pole numbers and the rotor speed together determine the frequency of the generator. So for the given frequencies, so if we would like to make the rotation speed slow down, we have to increase the pole numbers, so that we can use the slow rotations with multiple pole numbers to generate constant frequencies of the electricity. That's the meaning of it. Here we're showing you a 4-pole generator, synchronous generators. Now here on the rotors, we have the rotors here. So we have a 4-pole coilers generated here. So and the poles, no pole to no pole to sub pole, has been supplied with DC currents here. DC currents here. So we with field coilers, look at here, we have field coilers, 1, 2, 3, 4 field coilers, field poles. So okay, 1, 2, 3, 4. We apply the currents with directions, DC currents, so that we have no pole sub pole here. So we have the magnetic field generated, which start from the node pole and ended at the south pole. So the magnetic field generated here will be start from node pole, magnetic field, and ended to the south pole, and start from the ended to south pole. Okay, magnetic field. The rotor's magnetic field, which is a constant values, that start from node pole and ended at the south pole. Okay, this is magnetic field generated. So which is field coilers, in the poles. You look at the field pole here, the core materials be shaped as the shoes here. This try to making the magnetic field be uniformly distributed within the generators. On the stairs, here is the stator. On the stairs, so we have the slots. We have many slots. So in the slots, in and out surrounding the slots, we have the coilers. That is the armature readings. Armature readings. So here the armature readings on the stator and the field readings on the rotors. So arrange the readings on the armatures in different groups with different connections and different positions. It serves as the three-phase or single-phase generators. So that's the arrangement. Physically, it is like this. Electrically, look at here. So on the stairs, here is the rotor, right, which is the in series connection between the source. And on the stairs, we have several groups of coilers. Here, suppose we have 3 groups of coilers, A, B, C. So the A, B, C be connected in different way. It can be connected in star connection or dirt connections. For example, here so the A1 outputs, B1 outputs, C1 outputs. This is a star connection. This star connection. So the A1, A1, A2 coilers. So suppose the A1 is the starting points. So A2, the end points. This is the A pole, right? A pole 1, A1 1, A wave prime. So A2, so like this, and the B2 is separate. The B2 1, which of course, right, so connected, right, B2, and the B2 also connected to B1 1, B1 1, and the C2 and A2, A2 1. So this is because the A1, because it's the coilers. So anyway, in A, the end, to connect to the C end, and also the C end, the C2, C1, C2 actually is the end of the C, okay? So the E coil, E group coils ends okay. Okay, the figure showed here, which right, so showing that the E group and C group and D group, right, A group, B group, and C group, that okay, three group of coils on the stators be arranged in a star connections. Okay, they separate in okay, three different positions, which separate okay, by 120 degrees from each other, but okay, arranged in electric connection like star connections. Okay, internally. So this will be a right three-phase AC source a lot, okay, that outputs. So this is the field coils, four-pole field coil connection. This is the right three-phase stator, okay, armature coils connections. Of course, right? So this is one way, okay, arrange the connection there. So sometimes the connections not be okay, clearly see, right, when you open the generators, but be hidden in some parts of mechanical parts of it. And also the poles, core poles here, which not using a hole, right? Core materials, but using the so-called silent pole, okay, material, silent pole. Okay. So generally, we do not using a whole, right? The whole, right? Magnetic materials, cast steel materials as the pole. So usually the pole is okay, using several, okay, thin, right? Several thin steel materials to stack up, right? To stack up to form the poles. So that is the silent pole. The purpose of it is to reduce the AD current effects, because the silent pole that making the okay, each part of the magnet not right perfectly connected together. There are touching resistance between each piece of the okay, core materials. So therefore, making the AD current, the small ring current on the pole be smaller. Therefore, the core losses be smaller. Okay, that's the meaning of it, because the cast steel materials still be a conductor in comparison with the air, in comparison with the wood, comparison with the plastic, right? So although it is resistivity is much higher than that of the copper materials, which usually be used as the wires, as used the weedings. So the weeding materials on the motor or generator usually is copper. Okay, usually is copper, which is much better than steel materials. Okay. Now here I would like to emphasize that for all the generators, for the induction motors, for the transformers, that the weedings are using the copper wires. Of course, you can use the gold, right? So the gold is much better, but the gold is to cost, right? Cost much, right? So generally we're using the copper wires, while that the core or poles are using the cast steel magnetic material. So that's the difference between them. So both are conductors, but the copper is better, much better than the poles. So in such a way that we using the pole materials, we have to make the pole materials have a bigger internal resistance. That means the current cannot go through from one piece of the poles to another piece of poles, so that the AD current inside be smaller and the core losses be smaller. That's the basic ideas. So there are some detailed discussions on how to configure the silent poles, so which is not covered in these chapters. But if you are interested in, if you would like to become a good generator, good engineer to design good generator, you can read relative materials in some books. Okay, so that's the meaning of it. So here is one example showing you how the electrically connected the coils, field coils, both the field coils and the coils on the stairs here. If you read into some reference books, there are many other kind of the connections, but we cannot list it one by one here. Now we touch the principles. Actually, we already learned about the principles. Where we're talking about transformers. Okay. Now here, so we try to clarify that these concepts of the synchronous in the transformer. So both the primary and the secondary has the same frequency, exactly the same frequency. Okay, so the input electricity has the frequency, say 50 Hertz. The output electricity at the secondary has also the 50 Hertz, exactly the same. That's the synchronous. Now, in the motors, we have two types of motors. One is the induction motor. The other one is the synchronous motor. Induction motor is a synchronous motor. We have the also have the synchronous motor. Okay, because in practice, right, in most of the cases we're using the induction motors as the power motors, because there we just use one electricity. Okay, so we apply the AC electricity on the stator so that we have induced current on the rotor. Therefore, there is a rotation there. So that motors, okay, we call it a synchronous motor because that's the field, okay, magnetic field on the rotor depends on the rotation itself, depends on the inductions, which changing with the rotation, which change with loading. So as a result, okay, so the induced currents, the frequency of the induced current on the rotor has different, right, frequencies with that on the stator we apply. And also the rotor speed, okay, is different from the rotation speed. Rotor current frequency is different from the synchronous speed or we say the stator current frequency. Okay, so for the induction motors, obviously that the rotor speed, or we say the rotor current frequency, is different from the synchronous speed, or we say the stator current frequency, right? And for the synchronous motor, where the magnetic field on the rotors is produced by an additional DC current, okay, or external DC current. As a result, okay, the rotor speed, okay, is exactly the same as the stator current frequency. Okay, so we can configure the synchronous motors so that the rotor speed is exactly the same as the stator current produced rotating field speed. Okay, that's the synchronous motors. But synchronous motor, of course, has its pros and cons, advantage and disadvantage, right? So in the DC motor, we were talking about this one to showing you. Okay, that's why we do not use in the synchronous motor in the power motors, which are in induction motors. Because the synchronous motor, you can imagine that even it is rotating freely, you still have the big of the torques. That's dangerous. Okay, dangerous. Okay, so here that's why we're using the words and synchronous and synchronous. Okay, the synchronous motor, if the stator is connected to an AC supply, and the rotor will rotate at the synchronous speed. Why? Because the synchronous motor, that the rotor's magnetic field is not due to the inductions, but produced by external DC currents, okay, which we did not study in the generator motor parts, but here introduced to you. Okay, that's the meaning of it. So now you understand the meanings, okay? Because in the synchronous motors, we're using external DC currents generate a constant magnetic field on rotors. So once the stator be applied with AC currents, then the stator's magnetic field, which is a timely changing but amplitude constant, which actually is sine or cosine magnetic field, which rotating with the times, they interact with the constant magnetic field on the rotor. So as a result, there is a constant induced torques on the rotor, so making the rotor exactly rotate as the rotating field speed. Okay, that's the synchronous motor. But similarly, now for the synchronous generator, the generator usually so we're using the synchronous rotating speed to generate the constant magnetic field. Therefore, we have the constant output frequency of the electricity. Because in the generators, we would like to making the generated electricity has a constant and stable frequencies. Okay, if the rotating field, if the rotation speed of the generator is unstable, and the magnetic field of the unstable, then the generated electricity, the frequency is unstable. That's terrible. Okay. So that's why we really try to maintain the generator be synchronized. Okay. So synchronous generator, if the rotor is rotated at a constant speed by a prime mover, so look that the generator, the rotating speed of the rotor stably. So that's very important, which produce a rotating field, rotating field. So a sine waveforms of the voltage will be generated within the stator readings, as expressed by that. This comes from the Faraday's law, Faraday's law that we talk in the chapter 3 of the power energy theology. So constant rotating speed that determine the omega here. So the rotatings that generate electricity, which amplitude depends on 3 components. One, the turn numbers of the readings on the stators. And 2, the flux, amount of the flux through each readings. And 3, the rotational angular velocity omega. And meanwhile, the field, the electricity, which has a waveform of the cosine or sine waveform. The electricity has a frequency omega, which depends on the rotating speed as well as pole numbers of the field coils. And this is the instant generated electricity, the voltage changing with times, with a frequency, angular frequency omega. A root mean square values, effective values. Its effective values, which can prove to be root 2 pi, the turn numbers, flux density, and length. A 2 pi f, which is the root mean square values. This is root mean square values. Root mean square values equal to the E max values over root 3, right? Over root, right? Over root 2 equal to the maximum values, which you know that is the n phi and omega, right? This is the amplitude, okay, over the root, right? Root 2, okay, equal to the n, okay, phi, the omega, that is the 2 pi, okay, omega is the 2 pi frequency, F, right? Therefore, equal to root two and pi and number n and phi and A, right? That's it. Okay, root mean squares is the maximum values over root 2, right? Which we learned, okay, in the chapter 3 of electrology. And then here the maximum values is the amplitude here, which is the term numbers n with flux phi, which is the angular velocity omega. Okay, here, so over root 2. Okay, but you know that the omega, that is 2 pi f, right? 2 pi frequency. Frequency is the f, okay, hertz in hertz. So therefore, we have this one. We have this one. Okay. So where the phi is the flux, and the omega angular velocity of the rotor, and the turn numbers n, and the constant depending on the constructions of the machine. Okay. So meanwhile, the AC voltage frequency is given by, as I mentioned, okay, in the previous slide, that the stator generated frequency depends on one, the synchronous speed, and two, the pole numbers. Okay. That's it. Okay. Very similar. Okay. Which is the formula actually very similar for the motors. Okay, for the motors, where the synchronous speed, okay, depends on the pole numbers, which is the synchronous speed, which is the 4 pi f over the pole numbers, which is 120 I over. Okay, so there's the same things actually. So therefore here, so we can change the pole numbers so that for a given frequencies here, for example 50 hertz. So if the pole numbers is 2, so then this rotation speed must be how much is it? If is the pole number is 2, that this is 60. This is rotation speed. This is 50 hertz. So 50 hertz. So the rotation speed must be 3,000 rotation per minute of the rotors. However, if the pole numbers be 12, then the rotation speed we require is 50 times 10. So we just 500 rotation per minute. So we making the rotor 500 rotation per minute so that we can achieve 50 hertz of the generated electricity. And we can increase the pole numbers to 120. So that we need the rotation speed be 50 rotation per minute, about 1 second rotation per minute. Okay, 50, 1 second. That's okay. Practically, right? We used for some of the big generators, okay, power stations. Because you imagine that, okay, in the China we have a very big grid, right? Hydraulic, right? Power station, okay, with a big, right? Okay, in the three gauge area. So that rotation, the generators, rotors rotation, you can imagine, okay, it is very slow, right? Very slow. There, the pole numbers, okay, 100 pole numbers be there, 100 pole numbers. Okay. So now you should understanding how the electricity be generated, okay, inside a generator with the stator and the rotor, with the field coilers and with the armature coilers. You should understanding the combinations of the field coilers and armature coilers. So once again, the generated electricity here depends on one, the turn numbers, which is the physical parameters of the stator coilers or armature coilers here, and the flux, which depends on the field, right? Strength of the field generated by an external DC current, and the rotation speed omega, which is the rotor's mechanical rotations. Okay, these three parameters determine the amplitude of the electricity. Okay. Sorry. What's happening? I don't know. Anyway, so these three parameters determine the amplitude of the generated electricity, and the rotation speed together with the pole numbers on the on the rotors, so that determine the frequency of the generated electricity. So this is the major factors that determine the performance of the generators. Okay, here we have a summary on the characteristics of the synchronous generator. You should understand that one, the normal operation of a synchronous generator needs both a DC current on the rotor to produce a constant magnetic field and a mechanical power inputs from the rotors. Therefore, these two together form a constant rotating magnetic field. Okay. Now the DC current, the field current, no any electric powers at the stator readings be generated. Okay. So you should know based on these statements, expand these statements into the descriptions of the principles of the generators. So we need a DC current on the rotor readings to generate a constant magnetic field together with a constant rotating speed of the rotor form a constant rotating magnetic field. It is this constant rotating magnetic field cutting the steel coils on the stators that generate or induce constant frequency electricities on the stators. Depends on the arrangement and the group of numbers of coils on the stators. The generated electricity may be a single phase or three phase, the other polyphase electricities. This is the first point that we would like to convey to you here. The second point is that, so now the DC powers used to generate a constant magnetic field on the stator comes from a separate generator externally, a separate generator, or its stator readings. So because this is a generator, so the stator ammeter readings has the generated electricity there. Why didn't we use the generated electricity itself as part of the field currents? That's the concept here. Based on the source of the DC powers, we have two types of the generators. If the DC powers comes from the generator itself, we call it a self-excited generator. If the DC powers used to produce the field comes from a separate source, whatever, a magnet or a battery or a separate generator, that's generator, we call it separate excited generator. Therefore, we have the so-called separately excited generator and self-excited generators. So the separate excited generator, of course, it is very convenient. Why that is, sorry, the self-excited generator obviously very convenient, but separate generators has its own disadvantages. Generally speaking, both the separate excited generator and the self-excited generator have the similar characteristics in steady state, in steady running stage, but significantly different during their starting and under abnormal conditions. Okay, as we summarized here. So we have the so-called separate excited generator. We have the self-excited generator. Both have the similar characteristics in a steady state, but significantly different characteristics during their starting and under abnormal conditions. So here, just right as such understanding here. So later on, we explain to you. So to what extent there are different during their starting and under abnormal conditions. Now, to understand the principles of the self and separate excited generator, let's looking at the synchronous, and equivalent circuit of the generator first. Now, because we have the knowledge of the transformer and knowledge of the induction motor, so for most of you, you have no difficulties to understanding the equivalent circuit as we show here. Now, as at the beginning, I mentioned that for whatever generator, there are two important electrical coils. One is the field coils, the other one is the armature coils. First, the field coils. The field coils is supplied with DC currents generally. Okay, so the DC currents the DC voltage, so the currents field, right? We said the field currents equal to the field voltage over the field resistance because in the DC circuit, that the current voltage, right, the relationship is the right resistor. Yeah, resistor. Now, why we still right draw the inductance here? Because the inductance used to generate the flux. Okay, the flux okay. So the purpose of the right magnetic of the field coils here is to apply with the DC voltage and the DC currents to generate a constant flux linkage. Okay, so you know the flux linkage, which depends on the products of the fluxance, inductance. Here we use an LF to represent it, and the field current, which is the DC constant current, IF. So the product of it is the flux. That is the phi, flux phi here. Okay, so and the current depends on the voltage DC over the resistance RF DC. That's the current IF DC. Very easy to get to. So we have the field coils equivalent circuit here, which produce a magnetic field. So on the stator side, due to this magnetic field, so we have this magnetic field, that is the phi, big phi. The term numbers on the here is the flux, okay, flux linkage. Okay, the change rate, okay, which is the cosine, okay. Okay. So on the stator side, due to the rotation of the constant flux phi, they generate, okay, electricity with the voltage. The amplitude depends on the phi and rotation speed omega, and which changing with the times with the waveform cosine omega t here. So this is AC voltage. So here is the AC, right? AC okay. This EA here is the internal generated AC voltage. Remember this one, generated AC voltage. Okay, so field coil side DC, armature coil side AC generated here. Now, for the armature side, it has the small armature resistance. So the armature resistance. Once there is a current go through the armatures, then because this is the AC currents, the armature is coilless. Once there is a current go through the armature coilless produce magnetic field, that against the manifold, rotating manifold here. Okay, against rotating manifold here. So because you want to maintain the rotation here, this manifold try to armature currents, right? Current A produce field A that break. Okay. So the armature currents, if there is armature current, if the armature current is 0, that will be 0, right? So if the armature current is non-zero, then armature current produces a field, okay, armature current with armature field, we say the BA, that breaks the rotor. Okay, so you have the rotor rotating. However, once there is a current on the armatures, this current produces additional magnetic field, which against the field produced by the stator, by the rotors. So this field against the rotation of the rotor. In other words, this one try to break down, okay, the rotor. To maintain the rotation speed, you have to increase the rotating force. So increasing the rotating force means, okay, increase the torques to maintain the speed. So products of the torque and speed is the powers. So you increase the input powers. Now, so if the terminal current IA be 0, then there's no such a breaking. So the input torque is very small. So the input torque is just to overcome the frictions, the internal mechanical losses, right? So that's the case of it. Okay. So imagine that, okay? When the generator be open, although the rotor rotated there, but not consume powers because the input force is be smaller, the torque be smaller. Okay, that's the concept of it. So therefore, we define that the reactance or the inductance, okay, plus the frequency, the reactance of the armature coils has a reactance here that try to synchronize the rotation speed, okay, synchronize rotation speed. If there is no synchronizations, then this reactance disappear. Okay, no reactions. Okay, no the force against the breakings. Then this one disappear, right? Okay, so this is easy to understand. Therefore, the reactance here, which actually more or less similar to the linkage reactance of the armature coils. Okay, armature coils, similar to that, but the function is slightly different. No currents. Okay, these functions will be 0. As the currents increase, that cross the synchronous reactance here has a big voltage drops. Big voltage drops. Okay, so this is the output voltage. Okay, the output voltage equal to the internal voltage minus the voltage drops. The voltage drops will be the J X synchronous plus the armature resistance times the armature currents. Okay, so the terminal output voltage equal to the internal voltage minus the voltage drops across the internal impedance of the armature coils times the armature currents. Current AC, synchronous, right? Okay, impedance here, armature impedance here, and the internal generated voltage here, and the terminal voltage outputs. So this is the output terminal voltage. Here we're showing you a per phase equivalent circuit for three-phase generator. So all the parameters here is the per phase referred. Okay, so this is the per phase generated internal AC generation. This is the per phase synchronous reactance, per phase armature resistance, and a per phase output armature current, and per phase output terminal voltage of it. Okay, there are relationship between them. So very clear here. Okay, so generally, for the generators, the important issue is to maintain the frequencies output voltage be constant, and two, to maintain output voltage be a constant. Okay, so in practice, we try our best to maintain one, the frequency, and two, the terminal voltage, Looking at here, so for the frequency, okay, that depending on the rotary speed of the rotors, omega, okay. For the voltage here, so because the output terminal voltage equal to the internal generated voltage minus the armature, okay, voltage drops here. So the armature voltage drops depending on the output currents, that's the loading levels. So if the internal generated voltage keeps constant, the terminal voltage will changing with the loading levels. That's terrible. Okay, so in practice, we have to adjust the internal generated voltage EA according to the loading levels IA, so that the terminal voltage maintains at a certain constant. To do this, we have no means to change the frequency omega because the frequency be constant. And to maintain the terminal voltage, we have to adjust the field currents. Therefore, the phi here, so because the inductance, field coil inductance generally is a constant. And if we increase the current IA, the flux phi increase. The amplitude of the EA increase because depends on the products of phi and omega here. So by control the field current IA, we can control the amplitude of the EA. Therefore, can control the terminal voltage amplitude. That's why we have the field current adjustable which is used to adjust the flux phi in the air gap, then the internal induced voltage EA. It is controlled by a device. This device, we call it automatic voltage regulator. Automatic voltage regulator. Okay, so we try to control the terminal voltage by control the field current RF. Okay, according to the armature output current IA. If the output terminals be opened, we call it no load. Okay, so then the no load internal generated voltage changes against the field current RF based on the internal inductance LF. You know, the LF actually is not exactly a constant because it depends on the permeabilities of the core materials mu, and mu more or less depends on the current. So there is nonlinearities, which is the BH curve. Okay, BH curve. So here the internal generated voltage EA against the field current at a constant rotating speed omega have the characteristics of the BH curve depending on the permeability mu's. In simple formulas, that the internal generated voltage EA, which depending on the flux generated, flux density, and the rotation speed and the inductance. So K here is a coefficient related to permeabilities, related to the inductance, related to inductance. Okay. Simply speaking, that three prime factors determine the internal generated voltage. One is the inductance or permeability related constant, related coefficient. Here we use the K to represent it. The phi, which depends on the field current, So field currents, and the omega here, which depends on the movable, mover's speed. Mover's speed. So in practice, we can, by doing the experiments, to find out the using a separate excitation measures to test the characteristics of the internal induced voltage versus the field current for a given generators. This is the field current RF. Okay, so this is the open circuit terminal voltage. So internal. Okay, so in practice, if the terminal is opened, then the terminal voltage equal to the internal generated voltage because the current be 0. Okay, so that's the meaning of the open circuit test. So we're doing the open circuit test. Okay, so we can got, okay, we change the field current RF on the rotor side. Okay. Then we can monitor the terminal output voltage. So the terminal output voltage is the internal generator voltage. Now, if the generator itself is a star connection, what you measure is the 9 voltage. So this 9K, sorry. What do you measure? Always the 9 terminal voltage. So we're doing the test. So 9 terminal voltage over √3 for a star connection will be internal per phase in this voltage. If it is a direct connection, you know it is a direct connection. That K, you got to the pervadings, right? Voltage will be equal to the 9 voltage you measured here. Okay. So if you do not know the internal connections, you suppose it is a star connection, then you can determine the per star phase values VA. That's the meaning of it. The key is that, okay, when doing the open circuit test like this, you have to maintain the speed. It's running at the synchronous speed. So for all field current values, for different field current values, you have to maintain the speed be a constant. Otherwise, your test is incorrect because that the generated voltage is the product of the field currents, the rotation speed, and the characteristics of the inductance. Okay. Can be write into a constant. A coefficient, right? Chi, the field current, the rotation speed. So the chi, here is the a constant that related to the permeabilities or related to the inductance of core materials. Okay, field currents and the rotor speed. So for doing the open circuit test, maintain the rotation speed be a constant is a very important part of it. So then you will go to the open circuit, right? Okay, test here. So very like okay. So very like the BH curves for a magnetic core, right? So this is a BH curve here. So here for a small current, it is a linear paths. So for small field currents, relationship between the internal generated voltage EA and the field currents, if the speed is a constant, is a linear path, means that the chi here is a constant, just like a y equal to right ax. Okay, so this is a linear path, and when the current be bigger, so nonlinear paths. So that means the chi here for small IA is a constant. For big RA becomes smaller. For small, okay, generally speaking here, we're using the chi here, chi 0 here. So chi 0 is a constant for small field current RF, but it varies when the RF is bigger. That's the meaning of it. Remember this point. In practice, we can use in the generators in linear parts or the nonlinear parts. Both have the advantage and disadvantage. If a question said that this machine working in the linear parts, linearly excitation, that means the chi 0 be a constant. So if the field current at 1 amperes, it has a generated voltage 100 volts. If it is 2 amperes, it has a 200 volts. 3 amperes, it has a 300 volts, with the rotation speed a constant. When it comes into nonlinear one, so 1 amperes, so 100, 2 amperes, 150, and 3 amperes, 180. So nonlinear. That's the cases of it. So hope that you have good understanding on the these characteristics curves of the EA against the field current RA by doing the open circuit test. So open circuit test can help us to obtain the relationship between the internal generated voltage, the per phase voltage against the field current with a constant rotation speed. If you change the rotation speed, this curve will change. This curve will change. This curve will change. For each generator, you can, by doing test, get a group of such a curve at a different rotation speed. And a rating frequency. For any generators, you can get such internal induced voltage EA versus the field current IF curves and its rating frequency and rotor speed. Usually using a separate excitation approach. So imagine here, so for the same rotating speed, if the field current is the same, the internal generated voltage is the same. Okay. Which tell us the same field current produce the same internal voltage and a constant very important parts, right? We frequently used in the exercise or analysis of questions. You should understand it. So this, what does this mean? This means that which tells us that the same field current produce the same internal voltage at a constant rotor speed. So under whatever conditions, no matter how does the terminal loading changing, it is short circuit, it is the open circuit, it is full loaded, it is half loaded. If the field currents is the same, then the internal generated voltage is the same. Okay, right? In other words, if the internal generated voltage keeps no change, that means the field current keeps no change. Okay, except that you have changed the rotation speed omega. That's the meaning of it. Okay, so because this wording sometimes will appear in the exercise or examinations or the assignment. So we said that with the same field currents as the previous case, then now the loadings have been increased from 100 kW to the 200 kW. What happens to the terminal voltage? That's been way. This is the characteristics of the induced voltage versus the field current RA, which usually serves as the characteristics of the generator. So here now we have further explanations on the armature resistance and reactance. So one word that we use that for the reactance, we know the meanings of reactance. For the transformers, we have leakage reactance, and for the motors, we have the mutual reactance and leakage reactance. And here we also have the armature reactance. But this armature reactance, we do not call it as the mutual reactance, call it as the leakage reactance, but we call it as the synchronous reactance, because it's this reactance exists or appears when there is armature current, and we try to maintain the rotations. So as I just explained to you that once there is an armature currents, because the AC currents, so this AC currents generate instant magnetic field on the armature coils. This magnetic field interacts with the rotating field produced by the rotor or produced by the field currents. As a result, they try to break down the rotors. To maintain the rotor's rotation, one should increase the rotating torques to maintain the rotor speed. So this is the synchronous process. Once you try to maintain the rotations, once you try to synchronize the rotations, this synchronize is against the magnetic field produced by the armature coils. So such a process we call, because the armature reactions against the synchronizations. So that's why we call the armature reactance here as the synchronous reactance. largely speaking, the synchronous reactance, reactance is similar to the self-reactance of the armatures. So here, that's why we say, the synchronous reactance actually is leakage reactance plus the armature reactance. That's the middle way. So very similar to that, but a little bit different. Once again, remember that when we're talking about the reactance, inductance related to reactance, we link to the flux generated by the currents here, by current there. And also here, reactance also against to what extent you maintain the rotations, because it is the rotations that determine the frequencies of the generated current. If the speed changed, the frequencies of the current generated changed. The reactance values of the armatures also changed. That's the meaning of it. So this is the meaning of the synchronous reactance. For more details, you can refer to some of the books. There have further explanations of it. The armature resistance, which is the similar to that of the stator weighting we used for the motors, and the weightings we used for the transformers. When there is copper weightings there, the copper materials has resistance. That's it. That sometimes we also express the synchronous reactance in a per unit values, say 10% or 5%. In that case, the actual values is the per unit values times the base values. And the base values, which actually the base value here base impedance is actually the rated load So the base impedance here is actually rated load impedance. Look at here. So this is the generator's rating powers. So here is generator's rating powers. Here is 9 voltage. Terminal. For a three-phase generator, so VL here is the terminal voltage rating terminal 9 voltage square over the rating power generator. This is rating generator's three-phase total powers 9 voltage for 3 volt, which is the base impedance. This is also the actually is the rated loading impedance. That's the meaning of it. So the per unit values of the internal armature impedance means that the percentage of the armature impedance in comparison with the rating load impedance, which are a small part of that, less than 10% of that, 10% of that. Very similar to that for the transformer. So while the impedance of the transformer secondary side base values is also the rating loading base values. Okay, that's the meaning of it. Because here we just involve the two parameters in the armature coils. So we have the armature reactance XS, we have an armature resistance RA. Okay, the S here stands for the synchronous reactance. For the field coil side, it is a DC side. So we have the DC parts of the field coils. We have the AC parts of the armature parts. The armature parts, right? There is an internal generated voltage, which depends on one, the field strain produced by the field current, and two, that's the rotation speed omega, and three, the inductance of the field coils, which may change with the current. For small current, the inductance of field coils is a constant. For large current, the inductance of field coils becomes smaller and smaller as the current increases. Okay, that's the equivalent circuit of the motors, synchronous motors. Okay, so we stopped here today, and hope you have a good understanding on the principles of the test, and also the difference in terms of the equivalent circuit between the motor and the generator. In the motor, we have the equivalent circuit at two sides. Both sides are the AC related. But for the generators here, one side is the AC circuit, the other side is the DC circuit. And we not draw the two circuits together because they are different. Okay, see you this Thursday. Thank you for you all.